I think the question that people would want to ask is they can see the, you can see the specs, the things that we publish, the measurements that we publish, but what are some of the things that, our backers, our Geek Force members can't see but are important to the design of Geek Pulse?
All right, that's a very good question. All right, so as you can see, we have the bare board here, and we have the audio precision, the tests, a lot of stuff here, cables. So since we cannot see through the PCB, I would like you guys to see something in the real design file. That would be cool. So this one is the Geek Pulse X. All right, everybody knows that we have two dual mono ESS DAC IC here, but not only that, in the real board you cannot see through. It should be just like this. This will be roughly like the board you see. It's a simulation in 3D. I can even change that to say where's the red? Yes. See, it will look like very like the real board, right? But this is not important. The important thing is here. For the DAC IC, you need to get the best result. The master clock of each IC is the most important thing. So since we have two here, so we put a very important details here. Check here. These two are femto clocks. They output their master clock signal to this we call clock distributors. And clock distributor duplicate two clock signal, master clock to each IC, each DAC IC. So check this out. We have one straight line, one snake-shaped line. Why? Because we need, see my cursors here? This one goes to the left channel, this one goes to the right channel, and we want to make sure the two master clock line are both equal length.
So what does that do as far as how do you hear that?
Okay, if the master clock length is different, you will hear actually, because signal travel through the electronic wire still need time. So if the length is different, we will hear, actually people can hear slightly different between the left and the right channel on the master clock. So in order to get the best result for the sound, we need to make sure every clock line for the left, for the right are equal length. You see what's that? Ground wire.
What's that?
Ground wire. So it works like a ground. So a lot of poles surround the clock. So it will make sure that no noise can get into that clock.
Oh, it acts as its own shield?
Yes, it acts as a shield. So in a second, see, and the second layer. You see that?
Yeah.
It's a clock line and protected by a lot of ground wire all the way.
What else you got?
Okay, let me zoom out a little bit. We have many slots on the board. First one here, second goes here, third one here, the fourth goes here. Let me zoom in a little bit. Why we put a slot here? Because we want to protect a very important section. This section is the digital audio input. I don't want any outside potential power noise, even came from a Walmart or 12-volt switching power, will have any potential transmission going to this section. So this is a very important slot. Also here, clocks. We have clocks above. Clocks generate high frequency signals. It also becomes a noise going to an analog part. So we have a slot here to protect any potential noise going to the analog stage. And one more thing. We put a very big slot here and also a lot of caps. All this thing doing for one purpose, position-wise, protect the headphone output. So you can see the headphone output goes here. So every layout, every component's position has been strategized into the best place on the board.
So can we see the slots on the physical board?
Yes, here. See this, 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 and this.
All right.
What we see here is a 12-volt input. If you don't use the LPS, you will plug a switching 12-volt power input lit socket, right? So that's potentially become the most noisy part of the whole board. So this decides everything else. Why? Because we put optical here. The optical is relatively immune to the switching noise. And we put the digital audio input here, AES, balanced digital audio input here, and then the most important thing in the middle, USB. And you can see that, let me drag here, the distance between the XMOS USB receiver and processor with that USB connect is so short, very, very short. So we put the slot here, we put the physical distance as far as possible with the potential switching power to protect the USB input. And after that, we see the analog part, the balanced analog output. And in the end, we put the most vulnerable, less noise emitted single-ended analog output on the leftmost. So put the most distance between this one and that single-ended output. We are testing the bare board of the Geek Pulse with femto clock internal amplifier upgrades. Here is the audio precision. You can see the output direct get it from here, and we have the Lightspeed 10G cable going from the audio precision computer all the way to the DAC. All right, and we have a very normal switching power. We don't use the LPS here. So when we do the test, I won't show you the SNR, THD, this kind of thing that you can see everywhere. You will see in our test report. I want to show you something it's not easy to see. For example, here, a lot of people ask, okay, why your THD or whatsoever is different than the other guys tested. Let me show you one important thing. It's the bandwidth. If we test only from, okay, the only bandwidth is 22K hertz, you will see that the numbers become better. If we all go all the way up to 250K hertz, the more bandwidth we measure, we will see more and more noise and related stuff. You see, that number goes lower. But when everybody else, almost everyone, they only use 22K hertz as their standard, we usually use 45K or 90K. So you can see in this DAC, even in 90K hertz bandwidth, we measure all the way up to 90K hertz. The THD still perfect. It's the dB. You can see that in percentage. The other thing I care really a lot is about the ratio between the different harmonics. So here you're seeing this is a fundamental one. It's from minus 140 dB all the way to 0 dB. But you can see that the majority of the harmonic distortion is a second and third only. We don't have 6, we don't have 8, that's very little 10, but for the rest of thing is a very natural decay. So you will make your music sounds more natural. Let's talk about FFT. It's a very powerful tool, but you need to know where to see it. So in this example, we put the 1K standard frequency here. So you can see a spike, right? And for the rest, you see the majority of the distortion is a second and third harmonics. For the rest, you can see it's well below 140. If we use 140 minus 140 as a standard, everything's lower than that. And if I average that out, you will see that It's a very smooth, average out noise floor, happily laying down roughly 145 dB all the way here. And we see some little spikes here. I guess that's created by the switching power. Yes, and something here, always high frequency noise that we cannot get rid of by the switching power.
So when they use LPS, you'd expect that to be gone.
Yes. Okay, one thing I want to share with you guys. Although we produce a very wide price range of the DAC, from $199 Geek out to $1,000 of Geek Post to $130,000 of Sire. Price different and the features are different, but there's one thing I will tell you, I will keep it intact. Everything the same. It's our design principle and the philosophy behind it. We won't cut any corners if only that price is lower. We don't compromise.